carried out on the beamline. In particular, I'm going to look at the reactions of the Criegee intermediate, which is a difficult little beastie which has been postulated since the 1940s and 50s, but no one had seen it until we carried out this work. So I was told, not everybody is atmospheric scientists, so I was very mindful of that when I came with the talk, so I'm going to go through a bit of the drivers and why we're doing the work that we're doing. Some of the background to try and set it in context as well, then the actual experiments that we did, and I've got a couple of atmospheric implications. First off is one that we postulated for the formation of sulfuric acid in the atmosphere. Hopefully that will become obvious why that's important. And then somewhere where we've actually done some measurements in the atmosphere of formic acid, and we think that's because of the Criegee radical reactions as well. And finally, a few conclusions. So, what are... Sorry, I need to get rid of that thing. It's gone. Good. So, main drivers should be pretty obvious. So, we've got global climate change. And in this particular instance, this is the Intergovernmental Panel on Climate Change, and it's trying to summarize the state of the science with regards to climate change. Anything that's red is basically causing a warming effect. And things I'd like to point out are these error bars here. So this is reflecting, trying to reflect some idea of the uncertainty of the particular thing. So in terms of ozone itself, tropospheric, that's ground level ozone. Want to point, that's about a quarter that of CO2 in terms of radiative forcing, so it's really good, important to understand that one. And in terms of aerosol, the error bars are almost as big as the overall climate radiative forcing is predicted out there. So it's really important to not only understand these processes, but try and figure out where the errors are. So then there's air quality. Basically, you've got your photochemical smog. Occasionally, this is just need NOx. So that's NO and NO2 coming out the back of a car and a bit of sunlight, and you're going to produce this photochemical smog. And even in the UK, we do get enough sunlight to produce photochemical smogs in Manchester as well. But I couldn't get a picture of it because they're not very often, but there you go. But we still do get them as well. Right. And then, of course, there's health. Part of that photochemical smog, you're going to produce aerosol, so that means anything that's not in the gas phase, basically solid particles, you're going to breathe that in, and that can have a health impact. When we had the heat waves in Europe, not in the UK, but in the rest of mainland Europe in 2003, there were a lot of increases of deaths caused by, they think, breathing and pollution. So in terms of drivers, it's very important for health as well. And one of the big uncertainties is the biosphere-atmosphere interactions. Everybody hears about it in terms of basically cutting down rainforests, and you remove your sink for CO2, so that has an impact in terms of climate. Also, the biosphere is not a passive thing. It can emit things as well. Perhaps what we do causes the emissions to increase, etc., by climate change. Also, we cause pollution from ozone. What that can do is attack leaves, etc., and that can cause crop damage. I think they've estimated about £2 billion worth of damage in the UK for crops as well. So pollution has a major impact in terms of productivity of crops too. Finally, the last thing that we ought to try and do is do weather prediction, and some of the things that we're emitting and where they're transformed in the atmosphere will have an impact in terms of the weather that we're going to experience, particularly in the formation of clouds. And a lot of research is focusing on that. So then what I wanted to try and summarize in about 2 slides is what we do and why we bother. So I'm going to concentrate my talk on the troposphere. That's basically where we live and pollute up to about 10 kilometers. So all that we have to try and do as atmospheric scientists is try and figure out why is something present in the atmosphere. And there's several things that we can take into account. First off, you can have transport from above in the troposphere, from the stratosphere. So that's really important in terms of ozone. But in the end, this is only about a few percent in terms of ozone budget, so it's not really that important. Most of it is produced in situ. We've got emissions that go into the Earth's atmosphere as well. So you've got biogenic emissions, stuff from plants, etc. And also you've got man-made emissions as well. So you've got to take those into account. So that's going to be your source term, and you're going to be, I'm a kineticist, so everything A is going to go to B, I'm afraid. So we're going to have a source of our compound, and then you've got to look at the loss processes, and simply balancing them out. So we can have a chemical transformation, so it's a loss for one of these species, and it's also a source for other things as well. And in particular for ozone, it's never emitted directly, it's actually formed by these chemical transformations. It's only a secondary pollutant. And the other thing we have to take into account is physical removal. This could be physical removal for plants, it could be incorporation into rain, etc. So what we've got to try and do is just basically sum all those processes up, set up a whole bunch of differential equations, and we should be able to predict our concentrations. Well, that's the plan. Anyway, so then what I wanted to try and say is, obviously it's a bit more complicated than that one, but I've tried to simplify it again as well. Just like with climate, the driving force for all the chemistry that we see is going to be the sunlight. The sun's going to basically break down some of the compounds that are in the atmosphere, and you're going to break a bond, and so you're going to produce a reactive species. That then is going to go and react in the atmosphere, and you're going to produce some sort of product. This could be something detrimental to health, or it could be CO2, or it could be nicely removing things away from the atmosphere. So we've got to get some idea of the oxidizing capacity of the Earth's atmosphere, try and predict the concentrations. Unfortunately, those reactive species are also very reactive, and what they can do is actually go back to where they started from. And what they'll do is they'll go round and round this cycle, producing more and more products. Some could be in the gas phase, some could be solids as well, some could be particulate matter as well, and that's really important. And what we've then finally what you've got is a termination product that basically reacting with something that stops the chemistry. And all that we have to do is figure out how many times you go in that cycle before the cycle is terminated. If we get that, we get some idea of our concentrations. So how do we go about doing it? So basically, what we've got are several strands to what happens in the atmosphere. You've got reaction kinetics. This is basically looking at the rates of formation of products or the rates of destruction as well. Then, as a chemist, I would say that's the most important thing, but of course you've got to worry about dynamics as well. Pollution gets pushed around by the wind, so we need to take that into account. And finally, you've got modeling, which basically takes into account the kinetics and the dynamics, and it should try and predict some concentrations. So the types of things that we've got is basically shiny instruments in the laboratory, and all that we're doing here is trying to simulate what happens in the atmosphere. And I'm also trying to basically persuade any young person that they want to be a scientist and try and get them to actually do some practical experiments in my lab as well. Safety people probably wouldn't be happy with my daughter being in the lab, but it was a Saturday, nobody knew anyway. So there you go. Now I've admitted it's being broadcast live as well, so I'm going to be in real trouble. So this bit here, the analytical science is really driving the reaction kinetics. A lot of the stuff we've done before, we weren't able to study these reactions because we couldn't see anything that was happening. So the analytical science is really important there as well. And it's also important as it provides us our own sanity check. We cannot do the control experiment in atmospheric science. We can't say, everybody off the planet, let's see what the concentration would be if you weren't here. So all that we've got basically is we have to go out there and measure it. And this is where we do the analytical science. And this is basically going around the Earth, trying to look at the interaction, for instance, with the cryosphere, and also do lots of things in terms of measurements on research aircraft as well. That's really important, because then what we can do is look at the transformation of the pollutants to start to look at regional concentrations and regional impacts of the pollutions that we're getting. So is there, just because of pollution in an urban environment, it could actually have an impact regionally as well. And those are the types of things that we've got to try and do. So it's only the combination of using the measurements and the reaction kinetics that we can get some idea of what's going on. And typically, this is a flight where we've flown around the UK. In this particular instance, we're measuring nitric acid. It didn't really matter. So we go out there and measure it. Then we go back to our modeling friends, and here we've got basically, this is the same data, just not in terms of time. And what we've got is the horrible browny colour here. That is the nitric acid. My student, he's colourblind, so these are the only colours that you can actually differentiate. So here it's looking pretty good. And then when we get down here, even for an atmospheric scientist, this isn't beginning to agree. We're going to say this really, we don't understand what's going on. So here, what we've got to try and do is figure out, is it the measurement? Is it a lack of understanding of the science? It's only by you basically going out there, doing the measurements, using that analytical science, and trying to understand the reaction kinetics that we can try and understand what's going on. So basically what I call this is the atmospheric science merry-go-round. And it just depends on where you are, whether you feel pressurized or not. A lot of the time, what people will do, they'll go out there and do some measurements, and they'll do some modeling and say, hey, guys, this doesn't agree. You're doing something wrong. Go back into the lab and get me some more numbers. And a lot of the time that will happen. So, but what hopefully I'll show you today is what we can also do is do some fundamental lab studies. That way we get some idea of the actual kinetics that are happening. And then, because we understand physically what's going on, we can get some idea of basically lumping reactivity together, etc. Because models can't cope with an explicit chemistry model. So we get some sort of parameterization, and then we can scale up to the large-scale models. And then we can basically say, because we've done our new lab studies, they don't agree again. It's actually made it even worse. So back we go again, and we do our measurements again and again and again. And it's basically, a lot of the time it's been basically the people doing atmospheric measurements have been driving the science, but hopefully now I can show you that it's the lab studies too that are really important. So most of my talk is all going to be about ozone. Ozone, I've already said, is a climate of war. I'll start again. It is a... I really can't speak today. It's basically, it's going to have an impact in terms of climate because it's going to absorb IR radiation. It's also really important. It's an oxidant in its own right, and it's a precursor to the dominant oxidants in the atmosphere, the hydroxyl radical and NO3. So it has if you look at the reactivity of ozone, it has a major impact in terms of the atmosphere because it's producing the soaps of the atmosphere. It's going to have an impact on if it's removed from the atmosphere or not. And also, ozone nicely reacts with these emissions, and you're going to go through an oxidation process, and it's going to produce aerosol. So these aerosol here are really important in terms of climate change. It's one of the biggest uncertainties in it as well. So we've really got to try and understand what's going on with ozone and what does it do in the atmosphere. In particular, if you look at the aerosol formation, it's really important for these species that are being emitted by plants. You've basically got terpenes and sesquiterpenes. These are quite low vapor pressure anyway. And as soon as you add ozone to it, you're going to add some functionality in there, and you're going to reduce the vapor pressure. And they're going to crash out straight away into the aerosol phase, so it could have a major impact in terms of climate. I think this here brings home the message in terms of these biogenic emissions. They're really important. So this is the total amount of carbon coming out of by plants. It's huge, dominated around the tropics. And if you look at anthropogenic, it is quite a large amount. However, it is completely dominated by these biogenic emissions. So we really have got to understand what's going on in terms of these emissions. How do they react with ozone? And this is where the Criegee radical comes in. So back in the 1940s, Rudolf Criegee suggested that this is what happens to ozonolysis. Basically, ozone had a 1,3 cyclo addition to a double bond. It then forms this ozonide, which falls apart. And you've got these Criegee radicals here, and these are very reactive species. And they've been postulated, and no one's actually seen them before in the gas phase. And it's the fate of these Criegee radicals that has a major impact in terms of the atmospheric chemistry that we observe. It could be important for HCOOH formation. This is basically one of the major oxidants in the Earth's atmosphere. It can actually generate that, so that's really important for that. It can also have a major impact in terms of acid rain because it can go on to produce organic acid. It's basically what happens to this that is really important. Also, it's very important for processing of aerosol, and this is one of those sins that I wasn't allowed to do yesterday where you ignore everything else. But what I wanted to point out here is, right in the heart of this are Criegee radicals. And it's the fate of those which is going to have the impact on what happens in the aerosol phase. And basically, they're postulating this is why there's so much aerosol in the atmosphere. It's because of these Criegee radicals. And as I said, no one had ever seen them before until we did these experiments here. So how do we actually go about doing our experiments? Basically, we initiate our experiments with a laser light. We break some chemical bonds. We produce a radical in our system. And then we try to detect it. And what we use is a time-of-flight mass spectrometer along with a VUV radiation. And basically, it's got the multiplex photoionization mass spectrometry, or now on, we're going to call it the Osborn Machine. That's stuck from a conference in the summer. So basically, this is David's machine. And what we can do is basically photonize our reaction mixture, and then we sample it into a time-of-flight mass spectrometer. And because we've got the tunable VUV, we can differentiate between isomers, and that's really important in terms of measuring these Criegee radicals. So if you look at these Criegee radicals here, this is acetaldehyde oxide, the ethyl derivative of its carbon oxide. And what you can see here is there are lots of different possible isomers. And we need to be able to differentiate between them. And it's basically this tunable VUV which means that we can do that. That's the major step forward for this. This is the type of 3D data set that David's machine produces. We can slice it up in one of several ways. First thing that we can do, we can slice it along the time axis, and this is a kineticist dream. What you can do here is basically you're going to look at your certain species being produced, and you can watch it decay away. On top of that one, because you've got the time-of-flight mass spectrometer, you can look at the products too, so you can assess the mass balance. That is really important in terms of looking at the atmospheric implications. But what really other important thing you can do is you can slice it along photon energy as well. And because you do that, you can then identify this particular isomer that you're looking at. So basically here what you can do, you can get ion signal against photon energy, and because you know roughly where you expect it to ionize for a particular isomer, you can identify it. And also from the shape of that ion signal as well, you can identify the isomer. So you can see exact mass, and because you know the wavelength of light that is shone onto that radical as well, you can identify what's going on as well. And that's really important for the identification of these Criegee intermediates. Right, so the key thing that we've done is actually come up with a generalized way of producing these Criegee intermediates. It isn't exactly how they're made in the atmosphere, but it's a nice, neat way of making them in the lab. So basically you get a diodo compound, we photolize it, and in the presence of oxygen, you're going to produce this Criegee intermediate. And this time we can actually identify it for the first time ever. So this thing here, that is actually the signal associated with the Criegee intermediate. And this is where you've got basically the ion signal against photon energy here. And the red line is the predicted, and the open circles is what we actually measured. And just to show that you can differentiate between vinyl hydroperoxide and the acetaldehyde oxide, basically you see if we had that other species, the onset of the signal would occur at much different photon energies. So we can actually definitely identify what's going on here. So we've definitely got the Criegee intermediate. So we observed it for the first time. And also, this way of doing it, it can be quite a large amount of signal, unlike the first method that we did to try and actually observe these Criegee intermediates. So now we've got it, we're going to be greedy, and we're going to try and do some kinetics with it and see what happens to it in the atmosphere. So here we've got the signal as a function of contact time. You turn your laser light on, you produce this carbon monoxide, and in the absence of anything else, it just disappears. They are reactive beasties, and they will disappear. And that's a lot of the reason why no one could actually observe them in the first place. They are highly reactive. But just because they're highly reactive, actually is very important for atmospheric chemistry, because it can do a lot of stuff in the atmosphere. Then in this particular case, we added some SO2 into the system, and it decayed away faster. And we added some more SO2, and it decayed away even faster. So, being a kineticist, again, I've lived for straight lines. So what we can do here is basically get decay constants against SO2 concentration, and we can back out a rate constant. And here we've got a rate constant of 2.7 times 10 to the minus 11. And then your units afterwards. This is really fast. In terms of what had been predicted before, it's a couple of orders of magnitude faster than it had been predicted before. This is really good. So this means it potentially can have a large impact in terms of SO2 chemistry in the atmosphere. And what we've done, we've also measured it in this other paper for the carbon monoxide, the simplest of these Criegee intermediates, and that was equally fast as well, 10 to the minus 11. Both of them are really fast, and both of them are orders of magnitude faster than they had been estimated. I say estimated before because no one had actually done this kinetics before. So as it's much faster, that could potentially have a large impact in terms of atmospheric chemistry, and that's where we went on to see what's going on. Normally I'm happy with a straight line, but this time what we want to do is actually see what are the products of this reaction. These are all done at about 10-ish torr, I believe, or maybe a bit higher. So this time what we can also do, we can change the energy and go to 13 eV, and we can look at the SO3 that's being produced as well. So what we've got is we turn the laser light on and our radical disappears. And at the same time, we get a decay constant associated with that one. We can get predict what the rise would be for this SO3. So what we've got here is we can actually show that in terms of the Criegee radical reaction with SO2, it actually produces SO3. So what we can do is we can analyze the kinetics in terms of the decay rate or the production rate as well. And what you can see here is for the carbon monoxide, the simplest system, it agrees very well. So it looks like this SO3 is the direct product from this reaction as well. And we can do that for the other system that we did as well. We did exactly the same procedure. We looked at the decay constants and the formation of these species and see, do we get the same rate constant? And in this case, no matter which way you're doing it, look at the SO3 rise or the decay, we get the same rate constant. That's pretty much saying that SO3 is going to be the product in this system, which is really good. So now we can actually say we produce SO3, and in the atmosphere, that will immediately convert instantaneously, as far as the atmosphere is concerned, into sulfuric acid. And that's really important for making these aerosols. So why is it really important? Basically, sulfuric acid has a very, very low vapor pressure. As soon as it's made, it's going to crash out and it's going to produce an aerosol. So there's different ways of actually thinking how the nucleation happens, but in effect, you have sulfuric acid, you're going to produce an aerosol. This then is a surface where you can get homogeneous nucleation, just sulfuric acid going there and getting bigger and bigger. Or the other thing is you can get low volatility organics basically condensing onto the sulfuric acid that's already there. So it will have a major impact in terms of the mass of aerosol that is observed in the atmosphere. And this is what has been done before. Basically, you get these banana plots, they like to call them. This is looking at the amount of nucleation or particles in the atmosphere as a function of time. And what you'll see is you get these bursts appearing just after sunrise. And they reckon this is all to do with the fact of sulfuric acid being produced. So, again, I'm quite a simple man. I like to try and get things as simple as possible. And if I can set up a whole bunch of equations that I can personally solve to see if it's going to have any importance in the atmosphere, that's what I'd like to do. And if you look back in old papers, When they first said that this reaction wasn't important, they just simply set up these sets of reactions here. They got assume the steady state approximation, and you can basically predict the amount of sulfuric acid that is going to be produced by this SO3 formation here. Bear in mind, last time they thought it was a couple of orders of magnitude slower than we have actually measured it directly. So it could this time have a major importance. So what we have to do now to see if it's going to be important is compare the only other source that we know of sulfuric acid in the atmosphere from the hydroxyl radical, the main oxidant in the Earth's atmosphere, and compare it to this new Criegee intermediate source of SO2 to produce sulfuric acid. So what I did was a thought experiment to think about how much alkene would you have to put into the system to react with ozone to actually go on ahead and be as important as this other route. And what you'll see here is a plot of the amount of alkene needed as a function of temperature. The amount of alkene needed as a function of temperature goes down because you've got the Arrhenius parameters associated with it as well. On top of that, you've got a competing thing associated with the relative humidity. As you go up in higher and higher temperatures, the absolute amount of water increases. And it really is, in terms of the reaction of what's going to happen to these Criegee intermediates, you've basically got a competition between reaction with water and reaction with SO2. They're the two main fates that are going to happen in the atmosphere because there's so much water out there, especially in Manchester. Okay, so the amounts of levels you're getting are 1.6 parts per billion. So these are quite realistic in terms of the concentrations that can be observed in the atmosphere. This is butene. We can do a similar approach for isoprene. You get exactly the same types of plots. But this time, the amount of isoprene that you need is slightly more. This is because it reacts slower with ozone, so you produce less of this Criegee intermediate. So you need to put more into the system to make it as important. And then you can look in terms of ethene, and this time it starts to get unrealistic numbers, 250 parts per billion. You might think there's no way there can be that much in the atmosphere. But nevertheless, we can still get, with a few hundred ppb, this Criegee source to be as important as the other source of sulfuric acid in the atmosphere. So then what I went ahead and did was basically looked at how much alkene is out there in the Earth's atmosphere in these measurements. These measurements will have all been done pretty much by GC. So these are going to be completely underestimate the amount of alkene that's out there. If you use 2D GC, you get all these different peaks that are there, and you actually say about 90%, they reckon, don't know how they come up with that number, has not been measured accurately with the GC. So these are lower limits. And what I've got here is ethene equivalent. So this is basically taking into account the reactivity. So that's all that I've done. And you remember, I needed about 100 parts per billion for this to be as important. And it's not unusual for you to get hundreds of parts per billion in terms of these alkenes in there. So there is enough alkenes out there in the Earth system to make these Criegee intermediates and they to be as important as the hydroxyl radical source. So I've done the simple method. Now what I've got to do is phone a friend, and then they can actually go ahead and use a proper model. So this is the Met Office model that we've used. It takes into account all the circulation. It has quite a simplistic aerosol chemistry in there, and it also has quite a simplistic chemistry in there too. It's got something called the CRI version 2. So this is basically lumping the reactivity of certain species in there. And all that we have to do is slightly modify this to include the Criegee intermediates. None of the models in there would have had it beforehand. So what we can do now is actually look at this new chemistry and see, will it really have an impact in terms of sulfuric acid production. So what I have done here, or what we've plotted here, is on the left-hand side, this is the sulfuric acid production you would get in terms of the hydroxyl radical. And then on this side, you've got what you would get from the Criegee intermediate with SO2. I always get annoyed with modelers when they put these plots up and say, oh, clearly it's a much greater amount of sulfuric acid that's being produced. I can't see from looking at these plots, so then I go, come back to me with the amount of change. So this is now the plot of the change of sulfuric acid that have actually been observed here. And we get up to about 100% change in certain areas. And where we're going to get most of the change is where there is still a relative amount of SO2, and there's lots of alkenes that are being produced. So you get loads of them in terms of South America, getting some in Africa as well. So what we're saying is there could be a major increase in terms of sulfuric acid in the Amazonian rainforest. But guess what? No one's actually measured any sulfuric acid out there. So what we've got to do is go out there and see this is actually happening. So what we're suggesting is, because there's much faster reactivity, we're going to have a much greater source of sulfuric acid that's out there. So what this can do is actually then go on to produce particles. So what we've got to try and do is try and figure out what is the nucleation rate. If you get into the game of nucleation rate, to convert it into absolute nucleation rates is an absolute swine, and everybody starts to have fisticuffs and say, my method's better than yours. But if you look in terms of relative amounts, you get rid of all those horrible complications trying to convert it into absolute numbers. So all that we've done here is looked at the relative amount of sulfuric acid that's being produced, and what you can then do is just use this simple equation here for nucleation. This isn't the be-all and end-all in terms of nucleation that's out there. You've got to the power of 2 here, and in effect that ranges from 0 to 2, depending on where you are in the atmosphere. And typically, what they said on average is about 1.5. But all what we've done here is use for the power of 2. We're not saying that this is the absolute nucleation rate. What we're saying is if there's going to be any nucleation, it's going to involve sulfuric acid. So no matter which method you pick, it's always going to involve sulfuric acid. So if you increase the sulfuric acid, you're going to increase the amount of aerosol that's in the atmosphere. And what you'll notice here is, surprisingly enough, where we have lots of that sulfuric acid, we get an awful lot more nucleation. In this particular case, we're getting up to 800% more nucleation happening here. So what we're saying is that we've done these kinetics, we've actually looked at it, and then looked at the atmospheric implications, and what that does say is you're going to potentially produce more aerosol in the Earth system. And then what we need to do there is look at the full implications of that in terms of climate and for the formation of clouds. So this time, hopefully, we've gone and persuaded a few more people to go and do a few more measurements out there of sulfuric acid. And recently in a paper in Nature, what they've done is actually in the Finnish forest, they've actually observed increased amounts of sulfuric acid out there, and they are attributing it to this Criegee intermediate. So it looks like now people are beginning to take it on board, and it is having an impact, and they can actually observe it in the atmosphere. So the next thing we did is that's a global model. It doesn't treat the aerosol chemistry very well. Just basically, it just crashes out, and then it's static. But what we've used now is WRF Chem, so this is a US model, and this time we can look at the regional impact, and it's got a much better treatment of this aerosol. So it's not just a passive system, there's a two-way interaction here, and it's a dynamic way of looking at the aerosols. And what we've done is we've had to increase the chemistry to take into account these Criegee intermediates, and we've added a few extra things in terms of how we get the partitioning to the aerosol phase as well. So here we've got a picture where we've run the model here, and this is basically over the UK and Europe. And don't forget, there should be virtually no SO2 because of all the EU regulations that have come in. We've had to reduce our SO2 emissions. So the SO2 emissions are really low. However, in urban environments, what you'll notice is there's still an increase in terms of nucleation rate. This is basically comparing it to the OH source, this new Criegee intermediate source. And wherever there's an urban environment, we've got alkenes in the system, and we can increase our nucleation as well. So this is basically, even in low SO2 environments, we're still going to have an impact. So this is really quite important for regional air quality as well. So we need the models to take this more into account as well. One thing to highlight here is this is a North Sea oil platform, so you get a huge amount of SO2 coming out of there, and we get an increase in terms of the nucleation as well. So that's where that little bit is there. It's not an island, it's actually a North Sea oil platform. There you go. So that's it for the our chemistry driving what's being, what we think should be observed in the atmosphere. So now what I went out to do is this Criegee intermediate. I said it's competition between reacting with water or SO2. If it reacts with water, it could potentially produce organic acids. So here we've got a picture of a satellite retrieval of the amount of formic acid that's in the Earth's atmosphere. And then what we've got here is the model predictions. And even just by looking at them, you can see there's a complete underestimate in terms of the formic acid that's out there. The models just don't get it right. And what got me thinking about this was, if you look at where the alkene emissions are, this is where the alkene emissions are, and this is certain regions where basically they underestimated the amount of organic acids that are out there. So is there any evidence, can we actually try and come up with some evidence for actually saying that these Criegee intermediates are having an impact in terms of the formic acid production rate? Again, we go back to here, and I've simplified it. There's a few steps to get to this one. But basically, this Criegee intermediate can react with water to produce some organic acids. So can we go out there, measure some organic acids, and see if we can attribute that to these Criegee intermediate reactions? That's what I went ahead and did this year. So basically, I piggybacked onto this campaign, which is called Clean Air for London. And this was an intensive campaign that's been running for about 2 years now. And we had 2 intensive campaigns, one in the winter and then one smack bang wallop in the Olympics. And you try getting a hotel for about 30 people when you're trying to do one of these things in the Olympics, it gets quite expensive. So we had to get a smaller amount of measurements in the summer. And basically, we've got several sites here, and what we're trying to do is what is the impact of the urban environment on pollution. And in this particular case, we're measuring all the key species like ozone, NOx, etc. What I'm really trying to do is focus in on these organic acids. Are we getting an increase from these organic acids? Does it make sense? Can we relate it to alkene emissions? That's really what I wanted to do. So these are the intensive campaigns that we did. And there's lots of other universities associated with it. And what we're really trying to figure out is what is the oxidizing capacity of the urban environment. Are our emissions having an impact on what's going on? Will it have an impact in terms of regional pollution as well? Because what we're trying to do here is link the meteorology and the chemical speciation to get some idea of what's going on. But I'm just going to focus purely on the organic acids in this particular case. I'd love to go out there and measure a Criegee intermediate, but we can't do it. The concentration you're going to produce are 10 to the 5 in the atmosphere, molecules per centimetre cube, a small amount. Just because it's a small amount doesn't mean it's important. It's the flux through it that's important. There's an awful lot of flux going through these Criegee intermediates. So I can't go out and measure that one, but what I could do is go and measure one of the products of one of their reactions. And what I'm going to do here is, in particular, I'm going to measure the organic acids. And I use this a chemical ionization mass spectrometer. In effect, all that you do here is you produce a reagent ion, you let that react with your species of interest to produce another ion that you can measure with mass spectrometry. And the main advantage here is that you can tune the ion molecule reaction so you can get specific to the things you want to look at, and you're doing it at much higher pressure than you would do with electron impact, and therefore you get much higher sensitivity. And I get parts per trillion in terms of limits of detection. That's really useful. So here we've got some of the organic acid measurements that we've done of formic acid and the summer versus the winter. One thing to note here is the winter is a lot less than the summer, it looks like, and these measurements that were done during the Olympics this year. This sort of makes sense to me because the emissions coming from plants are a lot reduced in the winter versus the summer. That's great. So that means it makes to make us think that these organic acids are being produced because of emissions from the volatile organic compounds coming from trees. That's looking really useful for that. So then what we've got to do, so if it's coming from these a photolytic source, i.e. from ozone, does it correlate with anything else that is observed in the atmosphere? So I've got a plot here of formic acid versus nitric acid. In this particular case, this was done in the summer. This is counts per second yet because we haven't really calibrated it properly, and we're just going through that procedure now. What you'll notice is that the formic acid nicely correlates with nitric acid. This we know has a photolytic source. And in terms of atmospheric chemistry, having an R squared greater than 0.5, everybody starts to jump for joy. This is looking really good in terms of, yes, we've got a photolytic source. So it's looking like these Criegee intermediates reacting are being produced by ozonolysis of alkenes and going on to produce this formic acid that we've observed. However, when you go to the winter, just when you think you understand what's going on, they throw you this curveball here. And you can see not even atmospheric scientists would say that that correlates. All right? So we really are in trouble here. We don't understand what's going on. So why is that? We had no idea why it was going. So we tried to understand what was going on. So what we tried to look at is the average diurnal cycle. And the summer versus the winter. There's a lot of error associated with these measurements. But in the summer, it sort of makes sense. You get it basically peaking after midday where the ozone production is increased. Then it starts to die down again as the ozone reduces as well. That sort of makes sense. So if you look at the winter, if you squint your eyes and look a little bit, you might just about be able to see a rush hour peak here and maybe here. One thing to note is in the UK we're getting rush hour peaks around about 8 o'clock. If we did that in Stockholm, we get rush hour peaks around about 7 o'clock. I don't know what that says about the workforce in the UK, but maybe we just get up a bit later. I don't know what it is. But it does look different from the summer to the winter, so perhaps something different is happening. So what we try to do is there a direct emission from it? So we all know from cars you're going to produce CO and NOx. So are we getting some sort of correlation with the CO and NOx from the formic acid in the winter? So what we then did there was basically produce formic acid against NOx, and you get what looks like a fairly good correlation. So in a lab work, you wouldn't say it was a good correlation, but in terms of field work, because what you get, you're actually quite happy with that one. So it looked like there is a direct correlation with NOx. So what we then did is then we actually made it simpler in terms of we looked at split it down in terms of rush hour peaks. So here we've got the rush hour on the 16th, and what you see, you get a really nice strong correlation in terms of NOx. And also we've got the size of these dots here correspond to the amount of CO that's being observed here. So when you've got big dots up here, we've got lots of CO, direct emissions from car exhaust. So we are seeing seems to be a nice strong correlation with both NOx and CO. And we do it for other rush hours, you get slightly different amounts of traffic, so you get different correlations happening. But there seems to be a direct correlation. So there seems to be a direct emission as well. So is there any evidence for that? And surprisingly enough, there is. Once again, it came from the same beamline, and it was basically looking at these ethenols being produced in the combustion process, and what they can do is go ahead and produce formic acid in the Earth's atmosphere. So again, we should have just listened to what everyone was doing here, and we would have realized straight away that there was going to be some direct emissions. And what we think is happening here is that in the summer, you're getting the dominant source is from the ozonolysis of alkenes, and in the winter, because there's a lot less alkene emissions, the dominant source is flipping over to direct emission. It's still happening in the summer, but the dominant source is coming from these alkenes. That's swamping this direct emissions. But it's quite a nice story in terms of the kinetics, makes sense, and also if you go back and look in terms of the actual science, you see that there is some laboratory evidence for this direct emissions as well. And also it's a nice story because, as with everything in terms of atmospheric science, when you think you've got the answer, it isn't actually the answer. It's a combination of several things that produces the concentrations that you observed. So in terms of what's the impact of our direct emission and the secondary source, so this is where the most emissions we'd expect to get in terms of globally, in terms of Criegee intermediate plus water. And then what you'd actually get, if you, just the direct emissions, that's going to be dominated in the northern hemisphere. And then if you put the two together, what you see is to start to get pictures like this. So these are very, very quick runs that we've just done. But what this is beginning to look like is very much like the observations that have been seen out there in terms of formic acid. So the combination of this Criegee intermediate reactions and the direct emissions means we're getting much better in terms of being able to predict the amount of formic acid that's in the Earth's atmosphere. So finally, I'd just like to conclude and say we've actually, for the first time ever, looked at these Criegee intermediate reactions. This is really good. It's thrown up things into the air that we never thought would happen purely because of the enhanced reactivity. It's having a major impact in terms of sulfuric acid, and what this is basically trying to say here is it's also having importance with formic acid as well. I must have just stopped there. I should have actually said that. Sorry about that. We need to look at other Criegee intermediates, and next time we'll actually be doing that, especially stuff from isoprene, etc. These biogenic ones as well. Do they react as fast? This is based on two systems reacting as fast, and we're assuming that they're reacting as fast in the Earth's atmosphere. But we need to go out there and do it. On top of that one, it would be fantastic if we could actually look at these Criegee intermediates coming directly from ozonolysis. I don't think with this system we'll be able to do it because they're much slower reactions than we can use this system. And we actually, this time, we're telling them to go out there and do some more field studies. Go out there and measure your sulfuric acid in the rainforest, etc. That needs to be done. And hopefully, I've shown you by carrying out some work in the lab, getting some kinetics out there, you can actually postulate that there's going to be an importance, and it can actually start to drive the science. And it really is, once you've done that, that's great. You can go out there and do some observation, but it's only the synergy between both the field work and the lab work means you can actually drive it further forward to get a much better understanding of what's happening in terms of oxidizing capacity in the Earth's atmosphere. And finally, I'd like to thank everybody that did the work, but in particular everybody, Craig, David, Oliver, Archie, and John for the work that they did at the lab and let me loose on their system to do some pesky atmospheric science as well. And thank you very much for listening. We've only got an upper limit on that one, and that really has to be nailed down, because if we haven't got that properly, everything else will fall apart. Yes, and that's a really important one to measure. What we found is that's actually quite slow and can only measure an upper limit. So in terms of the impact of Criegee plus water, it's probably going to get, the SO2 is going to become more and more important because it's going to get slower. But we need to do that for other systems as well. Absolutely right, yeah. So we've done this at low pressure, and yes, we need to carry out some studies at higher pressure because you could get some other products being produced when you do it at higher pressures. The nucleation that we've done various models from like higher up in the upper troposphere, but a lot of it that we're observing is at the ground level. And the models that we've done since are at the ground level as well. we're talking tropospheric chemistry. If you go up into the upper trop, for instance, there's no water around there, so that it's going to get drier. So the Criegee reactions can be important there as well, but not plus water. And the direct emissions, we can't really say 100% hand on heart that it is direct emission. We can only say by looking at these correlations that this is probably is a direct emission in terms of this formic acid that's being produced. One thing I've not shown is we've actually done some measurements going around the UK as well, and we can unless we put a direct emission in there, we can't get an agreement with the measurements in terms of formic acid. You could say, hey, it's your measurements that are wrong, but we're pretty confident that we're doing it quite well. So we are getting the direct emissions happening from that one. But you can make it, most of your direct emissions are going to be at ground level, and I think a lot of your sources in terms of that's where the alkenes are. If you go up in altitude, they drop off as well. So most of it is going to be at ground level where this is being produced, probably in the boundary layer even.
I have one question. You had shown that the intermediates will generate a lot of aerosols, and that suggests that there's going to be an increase in cloud cover. Is there that kind of connection?
Yeah, but this is where we get into trouble with the aerosols. Basically, just because you can increase the nucleation rate doesn't mean it's going to produce a viable particle. And what we need to do then is say, okay, we've got an increase in nucleation rate. What we now need to go out is get someone else to go out there and model it better to see if it does make a viable particle or not. That's what we've got to do. But yes, it could potentially do that, because then once you make a particle, then it could become a CCN and make a cloud as well, potentially.